Hello everyone, I will be presenting low power dynamic circuit topology towards an amorphous IEGZO thin film ultrasonic transducer driving circuit. This work is done in collaboration with imec and MICAS from the TU Leuven. This presentation is for the FLAPS 2021 conference. Here a short self-introduction. I'm a PhD researcher at MICAS laboratories, currently pursuing my PhD. My research interests are thin film driving circuits for ultrasonic transducer arrays and energy efficient driving circuits for ultrasonic transducer arrays. Here's the outline of my talk, but I will just jump straight into my introduction. Ultrasonic driving arrays are used in many applications, ranging from medical imaging to ultrasonic haptic feedback. These applications implement large bulk piezo transducers in conjunction with PCB-driven circuitry. This creates bulky solutions with limited resolution, as you can see on the left-hand side. Now, other solutions combine MEMS transducer arrays with silicon integrated circuits, as you can see on the right-hand side. Both ties are connected by die bonding, and also these solutions prevents to have large transducer count or a large transducer array. Both solutions are bulky and expensive. If you want to enable large transducer arrays at a low cost, thin film display compatible technologies could offer as solutions. Here we could replace the MEMS transducer arrays processed in silicon by a thin film ultrasonic transducers. These transducers are produced in display compatible technologies. Not only the transducers has to be replaced, also the driving circuitry or the silicon-based driving circuitry could be replaced with thin film driving circuitry, enabling to integrate both the driving circuits and the transducers into a single thin film technology, which could enable us to create large transducer arrays at a low cost. Here, such a single film is shown, and actually, by producing it in a display compatible production, we are able to produce it for large areas at a low cost, significant lower cost than silicon solutions. Now, in order to fabricate this driving circuitry, we're actually using imec's dual gate-aligned amorphous IEGZO technology with a minimum channel length of 2 micrometers. Full processing and other information can be found in the following publication, but in this presentation we will not go further into detail about the processing of this technology. Most importantly, we should pay attention that it's a dual gate device and that we have actually a backgate here. By applying a certain potential at this backgate, we are able to influence DVT, as we can see on the right-hand side graphs. Now, if we apply a large negative voltage at this backgate, it turns off the device independently of the potential of the gate, as you can see also here. This will be further used in this work. Now, driving these ultrasonic transducers, we need to actuate this at a certain frequency, which is for these transducers 200 kHz. Now, if you take an equivalent model of these transducers, the most significant part is actually the capacitive part. So we have to actually activate a capacitive load with a certain periodic signal. Now, in order to do this, we have proposed here a circuit on the left top side. And here the most important of most stringent part here is the counter. As if we need to create a periodic signal to activate these transducers with a certain phase resolution, we actually need to operate this counter at a higher operating frequency than the oscillating frequency. Actually, you need to operate this counter at a power of 2 to the end faster than the oscillating frequency of the transducer. Not only the speed is important, as the transducers need to fit underneath the transducers, also the area is constrained, leaving us with the required specs as the following. where the operating frequency of the logic underneath the transducer need to exceed 3.2 megahertz, and also the area should remain underneath the 800 by 800 micrometers area. Now let's take a look at which logic topology could enable us ultrasonic driving. And here are different logic topologies given, but let's take a closer look at diode logic. Now, we can already see that the power consumption of diode logic is quite significant, and this is due to the static leakage power consumption of this logic topology. And this is due to the diode load on top, which always leaks when the pull-down network is pulled down. Now, not only the power, also the area is not meeting spec, thus the diode on top needs to be sized large to meet the speed spec required, or to pull up the device in a timely manner. Lastly, but most significantly, also the speed does not meet the 3.2 megahertz spec that we have set for our ultrasonic driving. Now, if we take a look at all the other topologies in literature and shown here, no of these topologies actually meet the ultrasonic driving spec. Now, in order to find the right topology that facilitates operating speeds required for ultrasonic driving, we can take some lessons already from CMOS technology. Their dynamic logic topology is already introduced to further increase speed of logic circuits and also decrease the required footprint. These logic gates work on basis of dynamic charges, and the output node of these logic gates work on dynamic charges. Here we actually pre-charge the output node, after which we evaluate by the pull-down network. If we translate this to an NMOS only technology, we actually place the PMOS on top by an NMOS. Now, a non-2 would look like this, where we have the pre-charge transistor on top and a footer transistor on bottom. So how does it work? We pre-charge the output node by the top transistor, after which in the next time step, we actually enable the footer transistor in order to evaluate the logic state by the pull-down network. Now, if we already have a backgate there to counteract process variation, we can actually eliminate the footer transistor. This is done by actually applying a very negative voltage onto the backgate in order to switch off the pull-down network and eliminate the footer transistor. So this reduces the size of the transistors in the pull-down network, eliminates the need of the footer transistor. Now, the big backgate is no longer statically it has a static potential, but now has actually a clocked signal on the backgate, which actually goes to a very negative voltage to disable the pull-down network and a slightly negative to counteract process variations. Now, we have to make a full counter of this logic topology, and here we have chosen to create a single stage logic, as cascading dynamic logic is very challenging. Not only the logic itself is important in this counter, also we have taken a look at the flip-flops themselves, and here we have chosen for dynamic flip-flops rather than the conventional static flip-flops you've seen in previous publications. And here we actually are using static buffers to retain the memory state of the flip-flop. Now, in order to output the carry bit of these counters, we actually had to implement an output buffer to drive the measurement equipment. Here we have chosen to use a differential logic output buffer to drive our measurement equipment with a capacitive load up to 4 picofarads. Now, let's take a look at the measurements of the counter. As you can see, the functionality on the right bottom side, each clock cycle, the logic state is actually pre-charged, after which the logic is evaluated. And on that point, we actually have a valid logical state. As we can see in the measurement here, the counter is actually counting correctly and the carry bit is outputting after 16 clock cycles. So we can see that the counter internally is working. We have seen that this counter is actually working up to 3.5 megahertz, which exceeds the required speed of the ultrasonic driving. Now, if we compare this with diode load logic, we can see that it's a faster logic. We can actually meet the required spec we're looking for, but also decreases the required footprint for our driving circuitry. The main disadvantage of this is actually that it's not standard logic compatible, so there is actually manual design effort needed to fabricate or design these circuits. So it's not compatible with a standard digital flow you've seen already in CMOS technology. To conclude, we're working, we have demonstrated working dynamic circuit topology operating up to 3.5 megahertz, enabling and illustrating that ultrasonic driving applications are possible in amorphous IGZO technologies. Future work will focus on improving on this design and integrate it into a single, in a full driving pixel design. Here are some acknowledgements and the references used, and I would like to thank you for your attention.